Hi, I'm Gary, and I want to show you how I use Cloudy. Okay, let's take a few moments to think about this model we've extended into the PDR. Before we go there, I want to thank two people who are here in the 2025 workshop who created two of the commands we're using. The option to use the Jenkins 2009 F-star formalism was done by Shamini Gunasekara in two of her thesis papers given here. And the large molecular hydrogen molecule was developed by Gargi Shah in her thesis in 2005. So thank you. Thank you for providing such a useful set of physical insights. This is the output from the simulation that went into the PDR. So let's just page down through it. This is all what we've seen many, many times before now. This is the first zone, the first set of hash marks here. We go on down, and we've gotten now to the end of the model, the shielded face. So this is almost 1400 zones in. The temperature has fallen down to 15 Kelvin. If you look at the ionization fraction, this is a hydrogen ionization fraction. The fraction of hydrogen is atomic, the fraction that's ionized. Where to go? There's no, it's not here as atoms. We go here, this notation here is the fraction of hydrogens that are in H2. So there's one H2, which took up, this is the ratio of the number of molecules divided by the total number of protons. And so 0.5 is a fully molecular limit. The grains were up at a few hundred Kelvin up here, 150 Kelvin or so. At the shielded face, we're deep in the cloud, they fall into 1800 degrees. It's still a bit temperature, a bit hotter than the gas. And there's our pause that we've added. So if we go down now, find the comments after the end of the model, that's a very interesting thing to look at. Okay, first the calculation stopped because AV was reached. That's what we set. That's a good thing. Some comments here. Cloud is thicker than a jeans mass. So the stability problems. It was constant pressure, so you need to rethink that. Probably the magnetic field would help out. The model was not quite converged. We only did two iterations. There's a thermal front in the model. So the cooling function has several inflections. One is around 3,000, 4,000 Kelvin. And what happens when it has to get over that inflection, the gas changes phase from about 4,000 down to about 1,000 Kelvin. So this is called a thermal front. It happened in the model, and the gas dropped from 3,800 to 355 Kelvin. So it's an order of magnitude drop in temperature. It's a constant pressure model, so the density would have had to go up to to compensate. You see, the density did in fact go up at this zone. Radiation pressure was part of the equation of state, and it looks like it was not quite converged. And these are not problems by themselves. It's just an interesting model. Um, Here's some other aspects of the molecular inventory. 100% of the hydrogen was in H2, 89% was in N2. GRN indicates grain surfaces. So this is water ice. So 60% at some place in the model of the CO and the even more CO, but of the water in the CO was in ground grain surfaces. So there's a lot of material here, and we will, some more molecules here. And we want to do now is go on and think about the spectrum that comes out. So I've already loaded the files and views. This is the spectrum of the H plus layer by itself. Let's turn on more visions of the spectrum. The model we just did included the PDR, and let's show that. So this is now in blue. So we've gone very deep in the model, a lot more visual extinction. So you'll notice the UV has been extinguished almost an order of magnitude more than it had been in just the ionized layer. So this emission, this energy has been taken down to the dust mainly. And you can see it's coming back out in dust. There's more thermal emission And you can see the ready genes tail is what's enhanced. The vene tail, the hot dust tail, is the same. So the hot dust is in the H plus layer. These both had that. What's present in the blue spectrum is that there's a lot more extinction and the dust is emitting more light. And it's cooler dust. And here's our CMB. You can see there's a very rich spectrum in the submillimeter. So these are probably mainly rotation transitions of some of the elements that are included in the calculation. Now, you'll notice the CMB is dwarfing part of the emission out here. And if you think about ALMA observations, you don't see the CMB. So what happens at an observatory is the background is automatically removed one of two ways. In the infrared, they frequently chop on and off the source, and the telescope reports on source minus off source. So if there's an isotropic radiation field, it's automatically removed. The other thing you can do is with the frequency chopping in the radio, where you look at one frequency, then nod off and go to different frequencies. And then any constant signal, if you take the difference of those, any constant signal will be automatically removed. So Cloudy can do that too. Your telescope probably removes the CMB without telling you. It's part of the pipeline. Cloudy has a command that will let us do that. Let's go back to our input script. So we want to, here we go. There's an option, no isotropic. So any isotropic radiation field is assumed to have been removed by this one of these two chopping mechanisms. So the CMB is the most important isotropic radiation field. It's described in this set of hazy. So we did that, and I can show you what it looks like if you exercise this option. So the green spectrum is identical to the blue spectrum over most of it. But when you do not add the CMB to the spectrum, now it is added to the physics. So the CMB can fluoresce rotation transitions of some molecules. I mean, you can see there's a lot of molecular transitions where the CMB is bright. And it's a true black body. The suppression of isotropic emission means that we can now see this radiogene's tail of the hot dust and all the rotation transitions that are out here. So there's a lot of ways to tease out information from Cloudy. There's a lot of information in Cloudy. It begins with the save commands, and then the next step is to have a look at Hazy to see the options that are there. Okay, so we have set up and run and looked at the spectrum of M16. Let's move on from there. Thank you.